can have our next speaker, Richa Rastogi, come up. They will be presenting work with Thorsten Joachims, both from Cornell.
Hi, everyone. Good morning. Very happy to be here. So I'll be talking about my work, which is fairness in ranking under disparate uncertainty. This is joint work with my advisor, Thorsten. All right, so as a motivation for this work, okay, there's just a little delay, I guess. Yeah, so rankings are very commonly used in search engines. And the purpose of the rankings in search engines is to focus the attention on the most relevant results. But when these rankings are used in high-stakes decision-making, especially when they're used in decisions to assist human decision-makers, it's even more critical that these rankings need to be fair. So in all of these examples, college admissions, hiring, housing loans, or clinical trials, there's a limited amount of benefit that needs to be allocated, or limited number of seats that need to be filled. And top K selection is often used to help the human decision maker so that they can focus their attention on those applicants and then select the qualified candidates. So in this paper, we study this phenomena of disparate uncertainty. And to introduce that, let me go through a first example. So we have two groups, Group A and Group B. Both the groups have the same number of candidates, so 2,000 candidates in both the groups. The relevance of the candidate I notate by Ri. It's distributed according to a Bernoulli distribution. And this is Bernoulli 0.9 for half of the candidates in Group A and 0.1 for the other half. Whereas in Group B, everyone is Bernoulli 0.5. So now if I have the task of selecting 100 candidates, and if we were to go by this probability of relevance, which is the Bernoulli parameter, then all of these 100 would be selected out of those 1,000 candidates, and none from the Group B. But we know that the number of relevant candidates in expectation is actually the same for both the groups. So that's unfair to Group B. And if we look at the posterior distribution for the parameter theta of the model, which is predicting these relevance probabilities, we would expect that Group A has these sharp and peaky posteriors, which are like beta distribution, and Group B would have relatively flat posterior because we have less amount of information, less number of features, less training samples. So that's disparate uncertainty in the sense that Group B has much higher uncertainty, whereas Group A has much lower uncertainty. We're more confident about their relevances. So the research question that we ask in this work is, how does this disparate uncertainty induce unfairness in rankings, and how can we quantify this unfairness? And then how can we mitigate this unfairness, or can we come up with a new ranking policy that doesn't introduce this unfairness, especially when disparate uncertainty is present? So the model that we study is as follows. There is a ranking policy pi, which computes a ranking sigma of n total candidates. And we're considering binary relevance here. So Ri is binary, 0, 1 of each of the candidates. When we're computing the rankings, we obviously don't have access to these true relevance labels. These can only be revealed through the human decision maker, which is the principal. But the policy pi has access to this predictive model of relevance, pi. And this is some model that has been trained using prior human decisions T and candidate features. And the principal goes through this ranking sigma from top to some position K, and their goal is to select as many relevant candidates as possible. So
Disculpa, ¿pueden ayudar?
Okay, so let me go through a detailed example. And in this detailed example, we have two groups, Group A and Group B. Their probability of relevance is at the top, and we have to select top 3 candidates. So I'm looking at the probability ranking principle, which is the optimal thing for the principal to do if they want to get as many relevant candidates as possible. And if they have to select top 3, they would just select these top 3 with the highest probabilities. And as I was mentioning, this would be unfair to Group B. So to quantify that, we say that we can compute this expected number of relevant candidates. Because it's a Bernoulli distribution, the number of candidates in expectation would, number of relevant candidates in expectation would just be the sum of the probabilities, so that for both Group A and Group B, there are 3 relevant candidates in expectation. We can also compute this lower quantity, which is number of relevant candidates in expectation given a ranking sigma. So this is PRP ranking at the position K equal to 3. So it's 2.5 because we selected these 3 candidates from Group A, and it's 0 because we didn't select anything from Group B. So now we can also formulate the cost of opportunity in rankings as the cost of missing out on the opportunities to be selected when that candidate was truly relevant. And the perspective we take is that the uncertainty in the predictive model, so Group B that was uncertain, that's imposing a cost on the groups and the principal. So that this cost is this cost of missing out on the opportunity either for the group or for the principal, overall for the principal. And so coming back to this example of PRP, if we compute these cost burdens, so we have these 3 stakeholders, the 2 groups, and the principal. The cost burden on Group A, we would expect it to be quite low because we've selected a high fraction of relevant candidates. We've selected 2.5 out of 3 relevant candidates from that group. It's not 0 because the other candidates still have some probabilities, and so there's still some chance that these candidates can be relevant. So there's a low cost burden on the Group A, but Group B has a cost burden of 1.0. And there's also a cost burden on the principal with 1 minus the fraction of relevant candidates that were selected from either of the groups. So you can imagine as the K increases in the top K ranking, the cost burden on the principal should go down because we should be selecting more and more relevant candidates. And the thing I want to point out is that these cost burdens are uneven among all the 3 stakeholders, so it is unfair. And after the fact, after the review, when the true relevance labels are revealed, for red unqualified and green qualified, the PRP principal does get all the 3 relevant candidates. So this is reflected in that lower cost burden to the principal, but it is unfair in distributing the cost burden. And so I want to look at the demographic parity in rankings. So in rankings, a predominant notion of fairness is proportional representation by size. So 4/5 rule, affirmative action, diversity-based constraints, and by size I mean some type of group size. So with demographic parity, we would be taking candidates in the ratio of 2:1 because there's 12 candidates in Group A and 6 in Group B. So that the top 3 candidates would be the 2.9 and 0.5. And if we look at the cost burden here, it's better than PRP, but it's still unfair because the Group A still has a lower cost burden as compared to Group B. And so for a possible solution to this problem of distributing the costs evenly, we look at uniform policy. So uniform policy is going to select candidates without any regards to the relevance and just randomly. And uniform policy in expectation would give equal cost burden. It would just be very high, 0.83 in this case. Note that this is also a stochastic policy, so this is many, many rankings and expectation taken over those rankings. But in high stakes decision making, we may not have that flexibility of drawing many, many rankings over. So the question that we ask is whether we can come up with a policy that has this benefit of having, like, distributing these cost burdens equally, like random lottery, but is much more effective. much more effective in the sense that it has lower cost burden on all of the stakeholders. And for that, first we look at the axiom of fair lottery, which says that in expectation, there's an equal fraction of relevant candidates. And this would be true for all prefix k of the ranking, so for all top k subsets pi k. And when we formulate those with the quantities, we would have this ratio, which is equivalent to group-wise fair lottery among the relevant candidates. So if both of them had the same number of relevant candidates, then we would pick the same proportion of relevant candidates. But if it was different, 2:1, then so on. So note that I'm emphasizing relevant here, and that is because we can now take these probabilities and predictive uncertainty into account. We then define the equal of opportunity EOR fairness in rankings. And for that, the delta EOR fair ranking policy is any policy that can satisfy this condition, which is to say that the fraction of the relevant candidates, the difference in them, is bounded by some quantity delta. And the EOR criteria, which we denote by delta of sigma k, so that's EOR criteria of a ranking sigma. That's the difference between this fraction of relevant candidates in terms of probabilities. So we're trying to get this delta sigma k towards 0, and that's quantifying the unfairness. And for that intuition, if you look at the group B, which has very high uncertainty, to get the same fraction of relevant candidates, we would need to take more number of candidates from group B. So that's opposite to what demographic parity would do. It would take 2 from group A and 1 from group B. But in the case, if we take 0.9 of the group A, then the fraction of relevant we would get is 0.9/3, which is 0.3, and for that we need to take more, like 2 candidates from group B. So with this principle of taking this delta to 0, we can first select the candidate from group B, where delta would be 0.17, from group A, which takes it to 0.13, and then when we take it from the group B, it gets close to 0, but it won't be exactly 0 because of some discreteness in the probabilities. And so with the EOR policy, if we now look at the cost burden, it's not only equal or more equal, it's also lower. It's much lower than the uniform policy. And so this then becomes a simple greedy algorithm that I'll talk about a bit. And yeah, so also if we look at the relevance labels that are revealed after the fact, then we do get 1 candidate that was not qualified among the top 3, but we still get 2 qualified candidates, and that means that the principal would need to go down further in the ranking. So there is a cost burden to the principal, but we do bound this cost optimality. So in summary, in this example, among all the different rankings, EOR is the only one which has delta close to 0 and cost burden that's approximately equal. We also compare it with many of the other existing ranking algorithms, including Thompson sampling and exposure that's very commonly used in rankings. And all of them, they have this cost burden that's uneven among the different stakeholders. And so the algorithm is pretty simple. It's a greedy algorithm. And what I want to point out is just that the selection criteria is based on selecting the candidate from the group, whichever of that is going to minimize that EOR criteria, and then pick the top candidate from that PRP ranking of the groups. So that then the runtime is also pretty small n log n. And we show this cost optimality in the paper. So this is the cost approximation guarantee for every prefix k of the ranking. So this is saying that the EOR fair ranking produced by this algorithm is cost optimal up to this amount. And what this is saying is that if we had a ranking that was very low had very low cost to the principal, but it also was satisfying this EOR fairness, then the cost of that cost optimal ranking and the EOR ranking would be bounded by this amount. And for this cost approximation, we use linear duality in the proof. We also extend it to multiple groups that I'll skip over in this talk. So going over the empirical results, this is for the synthetic data set where we simulate different levels of disparate uncertainty, high, medium, and low. And we're tracking the metric of unfairness, which is an aggregate metric of this EOR criteria, the absolute value of EOR criteria summed over all the positions K of the ranking. So EOR is the only policy that has this unfairness really low. It's lower than uniform policy because here, for fair comparison, we're comparing against one ranking of uniform policy, which has the median EOR criteria. Because one ranking, any ranking can be arbitrarily bad, but this would be like the median ranking. And every other ranking has significantly high amount of unfairness. For effectiveness, we're looking at the cost to the principal and comparing it with the provably optimal PRP ranking. So PRP ranking has the best effectiveness, but EOR policy is not that far behind. And if we look at a more granular, on a more granular level for each position K, so here, this is also for the synthetic data set, but on the x-axis, I have the length of the ranking, so every K, and on the y-axis, on the left plot, is that EOR criteria. The red one is the one that's close to 0, but every other policy accumulates relevance proportions. And the cost, we want to see overlapping lines, which we see with the EOR, but with the other policies, at least for one group, it's pretty bad. Even worse than the uniform for some of the groups. The total cost is the cost to the principal. Again, we want it low, which is the blue line PRP, the lowest, but the red line is not that far behind. We also have this for real-world data sets of US Census for the state of New York with this classification task of predicting income of an individual that we can then use it as a proxy. And what I want to say here is that we do it for like 2 groups where individuals have white or black African American racial group membership, and also for 4 groups, multiple groups, where they have Asian or other type of group membership. And in all of the cases, our results hold about distributing the cost burden more evenly and more effective rankings. And the final experiment is to show that EOR can also be used as an audit tool. So recently, ProPublica and the markup, they both asked this question whether Amazon was ranking their own products higher up in the ranking. And to do that, we formed these 2 groups of Amazon and non-Amazon products. We use the Amazon logged ranking, so logged ranking on the Amazon platform, and an open source model that can predict the probabilities of relevance. We calibrate that, and we look at the EOR criteria of the Amazon ranking, and also compute an EOR ranking itself. And at least for some of the positions, we see that the Amazon ranking prefers their own brand products higher. So this is not to say that it is a conclusive proof of unfairness, because we don't have access to the actual production model. So with that, I'd like to end the talk with the key takeaway that disparate uncertainty, it induces unfairness in selection processes. And I went over these items where we developed this EOR policy. So if this talk was interesting to you, please check out our paper for more details. Thank you.
Thank you so much, Richa. This was really interesting. And I had a question about, I found the example you gave about Amazon self-preferencing really interesting. There's also recent work I've seen that shows experimentally they might be actually self-preferencing. And I wonder if you thought about any follow-ups in which this kind of algorithms can like diagnose self-preferencing, perhaps in a more experimental setting, running some sort of a randomized trial to see how it would compare with other types of ranking that they might do, or any of the sorts. I would love to see this also done in practice, and I find it really interesting as you presented.
Yeah, I can maybe talk in more detail, but I think I think, like in that Amazon experiment, we can compute like a lot of these rankings, and then computing that EOR criteria as seeing this proportion of relevance that we're taking from different groups, that's relatively easy to compare. So as long as we have like these logged rankings, then we can do this. I think the key thing is that, so in this experiment also, if we can have access to a production model that's being used by Amazon, I think that would be the conclusive proof, and that's where we also caution against this type of analysis. But yeah, those are my immediate thoughts around that.
If we could get another round of applause to Richa.